Hi, everybody. Today we're switching to a new culture. We've done 3 cultures so far: Babylonian, Egyptian, Chinese, and now we are getting to the point where now we're getting to the culture that a lot of people mistakenly think is the beginning of math, which is the Greeks. So no, the Greeks were not the only people to be doing math in ancient times, and they are not the first people to do it. And they did not make up a very good number system in Greece, so they didn't do a lot with like their algebra, number systems, and arithmetic, and things like that. But the Egyptians do deserve a lot of the credit they get, because the math that they made was really sophisticated, and their geometry that they started putting down around 500 BC, and by the time of 300 BC, they had created a system which has been in use now and still is. Students still take geometry, and the geometry that they take follows the model of the ancient Greeks. Well, with ancient Greece, we also get famous, we get people. So why don't you type into the chat, do you know the names of any Greek mathematicians? Okay, I see Pythagoras and Euclid. I see Archimedes, Eratosthenes, who was astronomer and did geometry also. Okay, well, good. Well, it looks like we got the big 3, who are Pythagoras, Euclid, and Archimedes. There are 2 more I'm going to add to this list. So around the time of Pythagoras, you have someone named Thales from about 500 BC. And Thales wrote the first geometry book and put down the first set of postulates and theorems. And Pythagoras was there around 500 BC also. Now, Euclid is one of the most famous names in geometry. Euclid wrote several books, the most popular of which, does anyone know what the book that Euclid wrote? It was really split up into chapters that were called books. They were the 13 books of, anyone know? Yes, I see there, the Elements. So Euclid wrote a book called The Elements. And this is a book that is, aside from the New Testament, it is the most published book in the history of the world. So in a sense, it's like the Bible of geometry. And what you should know, and so it's called The Elements, and you could buy it. You can go on Amazon and buy a copy of The Elements. Usually it's in, they split it up into three volumes that you buy for about $10 each from Dover. So you can own The Elements. You could buy it as one big book, also. Euclid himself is actually not, he's considered to be a great writer and collector and just teacher, basically, putting stuff down, organizer of math. But Euclid himself is not like really considered to be a great mathematician, in the sense that not much in the Elements is originates from Euclid. He took the other elements. They always called these books the Elements. So for hundreds of years, people were writing books called the Elements, and Euclid wrote one that sort of compiled all the information and organized it. And he organized it so well that it became the second most published book in history. And it was in continuous use from 300 BC until still. It is still being used. And there are like private schools mostly that like emphasize the classics, and they'll use the Elements as their geometry textbook. And the Elements is pretty readable. At least the first like third of it is pretty much what you learn in geometry class in whatever grade you take geometry in New York. You take it in 10th grade. Some students take it in 9th grade. But you can follow it pretty well, the Elements. All the things about triangles and circles. That all happens in books 1. There's 13 books, but they're more like chapters. Book 1 is a lot of high school geometry, and book 3, 4, 5, those 4 books cover most of what you do in geometry still. But there are people after Euclid, and Archimedes is, we're going to do an entire day about Archimedes. I think it's not tomorrow, or 3 days from now, I believe we'll do an entire day dedicated just to Archimedes. So Archimedes is considered to be on everybody's short list of greatest mathematicians of all time. Often they put Archimedes and they put Isaac Newton and they put someone named Carl Friedrich Gauss. Well, Newton and Gauss were in the 1600s and the 1800s, late 1700s. But Archimedes is 250 BC. We'll spend a whole day on Archimedes. That's coming up. Today, it's mostly Thales through Euclid. But Archimedes wrote about 13 mathematical papers that we still have copies of. And they are really sophisticated and clever. But after Archimedes, the next generation, the great geometer, as they call him, named Apollonius. Apollonius wrote a book about parabolas and ellipses and hyperbolas. They're called the conic sections. And that book is extremely hard. I once went through a phase where I thought I would go back to like the oldest time of math, you know, like Thales, 500 BC, and just try to master, you know, everything and see how far I could get. And it was getting Euclid. Some of Euclid's elements is pretty hard, but it's okay. Like if I spend a lot of time, I was a math major in college, I could get through, I think, all of Euclid's elements. But Archimedes is getting like way harder. And I thought I would go through Apollonius's book, and it was too hard for me after I got about a quarter of the way through. I was not making much progress. So it's pretty amazing. That's 200 BC. There's still 2,000 years of math happen after that. There are other things in math you can study besides Apollonius, you know, later on. It's not like you have to if you can't do the Apollonius, you can't learn any more about history of math. But that book was seriously difficult. Okay, today I'm going to take you through some early geometry. And for some of you, it's been a while since you've done geometry. Just as like maybe like a show of hands, if you go to the participants list, you could like click yes, no. If I say something like side angle side, side side side, what is, when you think of that, click like yes or no. Are those things that have any meaning to you, or have you forgotten, like you're like side side side? Like what does that even mean? Click yes if you know, if I say side 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 and you're like, oh yeah, I know what you're talking about. And click no if you forgot what that is. It's okay, because there's no prerequisite for this section of this course. Okay, so some people didn't vote yes or no. Of the people who voted, most said yes. But if you didn't vote at all, does side, side, side have any meaning to you? And it's okay if you forgot. Don't feel bad about that. I'm not, as I said, there's not a prerequisite of geometry. But since the next 4 classes, this is our biggest unit, 4 days of Greek math. And there are some fundamentals of geometry that I want to remind you of. Don't feel bad if you forgot. Okay, some people didn't vote at all, so I'm concerned that those people are like maybe here, maybe they're not at their computers right now. Okay, well, I'm going to start with Thales. There is something called Thales Theorem. That's because Thales wrote before he wrote the first book, which is now lost. All the Elements books that other people wrote before Euclid, those are gone. Those have not, they weren't deemed worthy of copying down anymore because Euclid's Elements was so good. So we don't have Thales Elements. All the hundreds of years of people writing books on the Elements, those are all gone. There's people writing about them sometimes, but we don't have those anymore. Thales Theorem, Thales came up with a couple of theorems, but the one that's known as Thales Theorem is this. You have a diameter of a circle, and you have a point on the circle. So these 2 points are on the diameter of the circle, and this is just some random other point on the circle. And the question is there a way to calculate out the measure of that angle up there? Now, oh, you can't see the drawing? So what I've drawn, all I did so you don't see the Thales theorem, the circle. I only drew some highlighting on 3 of the points, and I put a question mark. Okay, so most people do see it, so maybe go out and then come back in. Okay. Now, I'm going to show you a very cool website that I want you to be aware of. I'm going to go over to the browser. And there is a website that's called Desmos. Now, Desmos, maybe you used it as the graphing utility, but if you do desmos.com/geometry, you get this drawing program. And with it, this is called a dynamic drawing program. There are different versions of it, like there's one called GeoGebra, and there's something called Geometry Sketchpad. And here's the way it works. You have these tools here. So if I want to make a line segment, I click once here and I move and I click here. Now I have a nice line segment. But if I go back to this select tool, I can actually, like a rubber band, I can change the points that define the line segment. Then I can come here, more tools, and I want the midpoint of this line. So I go to midpoint, and I click on the line segment, and it makes the midpoint. And then when I come here, if I change the original 2 points, the midpoint moves also. Maybe you've seen something like this with Geometry Sketchpad or GeoGebra. GeoGebra is like very advanced and hard to use. For our purposes, desmos.com/geometry is going to really be useful to illustrate this stuff. Now I click on the circle tool, and you click on the center of the circle, and then you move to where you want. And then if you go on top of a point that already exists, it like snaps to it. So now I have a nice circle. And check it out, if I move the one of the 2 initial points around the circle, changes also. The midpoint changes. The midpoint is based on the segment, and the circle's based on that. Then I can come here and say point. And if I move onto an object, see, it kind of snaps onto it. And now if I make a line segment from here to here, I went from here to here. Now, in the comments, what does this angle look like, at least for the dimensions I have now, this angle that I'm pointing to? It does. It appears to be a right angle. And I think I can measure it. Choose a point. Okay, so you choose a point on one leg. You choose the vertex. You choose a point on the other. And you can see, oh, actually, this would have been better. Let me go back. Instead, I'm going to measure angle by clicking on this, this. And as you can see, it is 90 degrees. At least this one is. But check this out. If I go back to the select tool and I take this point, it was constructed to be on the circle. So when I move it, it stays on the circle. But check this out. And that is called Thales Theorem. Thales Theorem, which is hard to say a bunch of times fast, says that this will always be a 90-degree angle, as long as the diameter of the circle is one of the points, or diameter of the circle is one of the sides, it will always be a right triangle. It's pretty surprising, Thales Theorem. Let me show you how to prove it. I'm going to go back to the iPad now. On the screen, you see a diagram. And let's say, let me put some numbers in here. I'll just call this number 1, number 2, number 3, number 4, number 5. What I have here is a triangle. This one. We don't know that angle 1 and 5 together are 90 degrees yet. I'm going to prove it. Not just that it looks like 90, not just that Desmos geometry says it's 90, but I'm going to prove that angle 1 plus angle 5 must be 90. And to help you out, I'm saying, let's just say for now that this angle in the corner is 50 degrees. Is there any other of these 5 angles, 1, 2, 3, 4, 5, that you can now say with certainty how big it is, like how many degrees it is? Yes. Wait, sorry. 3 is not 50. No, 3 is obtuse angle. 5 is 50. 5 is actually not 50. How about this? What angle is 50? What other angle must be 50? Let's ask it that way. There is another 50-degree angle in this picture. Well, that's 2 and 3 do add up to 180. That's true. But which other angle is, so we don't know 2 or 3 separately, but together they do add up to 180? Yes, Stephen E., why is angle 1 have to be 50 degrees? That's right. You see, these triangles in a circle, all radii are equal. That's what makes it a circle. So this, this triangle that I'll make orange, that's an isosceles triangle. An isosceles triangle has 2 equal sides, and the base angles are equal. So that makes, if this is 50 degrees, angle 1 is also 50 degrees. Now, what should angle 2 be in that case, and why? Okay, angle 2 is 80 degrees. That's right, I see. Because the 3 angles of the orange triangle have to add up to 180. So 50 plus 50, we have those already, plus what equals 180? Well, that what is 1? Well, it's not 100, it's 80. Now remember before Nina mentioned that angle 2 and 3 together are 180. So that makes angle 3 have to be 100. Now, how about this obtuse triangle on the right? The one that has angles 3, 4, and 5 in it. What can you say about that? That triangle with 3, 4, 5 in it. What do you say about that? That green obtuse triangle. It's got the 100-degree angle in it. What else can you say about it? Yes, it's isosceles also, because again, both of the sides are radii. So that means 4 and 5 have to be equal, but together they have to be 80 because the triangle has 180 degrees. So those are 40 each. And the 50 and the 40 together become 90 degrees. Well, that shows that it's true for the 50, if it has a 50-degree angle, this must be 90 up here, but that's not like generally proving Thales theorem. So let me erase this and go a little more generally now. If I call this angle A, this is also A. This thing is 180 minus 2A. And that makes this angle 180 minus 180 minus 2A, which is just 2A. Remember how these were both 50 and that was 100? Now, hold on a second. I'm going to call this angle B right now, just to call it something. And this would be B also. Now, if I look at the large triangle, the big one, not those 2 pieces, but the big one, it has 3 angles, A, B, and A plus B. So, but those three angles have to add up to 180. So A plus B plus A plus B has to be 180 degrees, which is 2A plus 2B equals 180 divided by 2, A plus B has to be 90. And that's our standard proof of Thales Theorem. The only math that you needed to know for that theorem are that in an isosceles, well, you have to know that all radii of a circle are the same length. You have to know that in an isosceles triangle with two equal sides, the angles across from them are equal. You have to know that the three angles in a triangle add up to 180. And those are the only three math facts that you need to know to understand that proof. There's a theorem I just want to mention. Here is like this is not an isosceles triangle. Let's say this is 50, this is like 70. Can you take a second to figure out what this obtuse angle, it's a straight line, what would that obtuse angle have to be? And some of you maybe got there through two steps. Maybe first you figured out that this was 60, and then use the fact that these two angles together make a straight line to be 120 is the answer. Well, I do want to let you know that there's a theorem. I'm not going to load you down with too many theorems, but some of these theorems are going to come in handy. So here's like another one to add to the list. There's a rule that the exterior, it's called an exterior angle. Where's my highlighter? There it is. The exterior angle of a triangle is always equal to the sum of what's called the two remote interior angles. So if you ever see this situation, by exterior angle, I mean that if you take one of the sides and you extend it, this angle, if this is A and this is B, this will always turn out to be A plus B. That's called the exterior angle theorem. It factors into one of the proofs tomorrow. We could have used it over here also. See, we could have jumped to this being 2A without going through the 180 minus 2A part. If you knew the exterior angle theorem, you could see that this is the sum of these two. So then you wouldn't have had to do this either. Okay, so that takes care of Thales theorem. And I do think one of the homework questions is literally just showing you a triangle inside with the diameter being one of the sides and asking what's the measure of that angle. Okay, so that's Thales theorem. Now I want to skip into some things that are related to similar triangles. Today is a lot of geometry review that you'll need to understand the next 3 days, because we're going to be looking at some complicated math. If the next 3 days, 2 or 3 days, could be kind of hard. Oh, hold on one second. Don't get too scared, because it's I'm going to go through this carefully, and if it's seeming like it's too hard, I don't have to do all the different subtopics that I have planned, but this is the pace that I want to be going right now. So These are similar triangles, and they're right triangles. How do you calculate out x in this situation? That's right. We're going to set up a proportion. Take a minute. Some of you haven't, it depends on what math you've done recently. Why don't you take a minute to calculate out what x is? It's going to be bigger than 4, but how much bigger than 4? Take a minute on that. Okay, I see a lot of 4.5s. I like to set up proportions this way. 9 over x equals 8 over 4. I like to put the numbers from the same triangle together. Some people might like to do 9, like corresponding parts, 9 over 8 equals x over 4. You get the same answer, but historically speaking, the Greeks would more likely do it this way, because they would think, okay, 8 over 4 is saying that the ratio is 2, like this bottom side is double the length of this other side. So like, even though other proportions would work, the fact that this proportion becomes the number 2, which tells us about like the shape of the triangle itself, where if I did 9 over 8 equals x over 4, that ratio, 9 over 8, would tell us the relationship between the two triangles. Anyway, you do get 36 equals 8x, so x equals 36 over 8, which is 4.5. Okay, so proportions is another thing I'm reminding you of. Now, here's another picture, but this one's going to be kind of funny because I have 9 and x just like I did before. And I have 4 here. These triangles are the same, they look the same dimensions as the other ones, but this is more like general. Check this out. I'm going to put an x over there. So the answer is not 8 anymore. So what I'm telling you is that this side and this side are the same length. Is that possible? Is there a length for x that would make that happen? Well, go ahead and set up the same proportion and watch what happens. Okay, and I see a bunch of 6s. That's right, because if you say 9 over x equals x over 4, and then you sort of so-called cross multiply, you get x squared equals 36. Well, x has to be positive. And now comes a very important picture. You'll want to copy this picture down. This is a very important configuration of lines. I have a right triangle, ABC. It's oriented so that the hypotenuse is horizontal. This would be true even if the hypotenuse wasn't horizontal. But usually when they draw this picture, they draw it that way. And you see that line segment, there's a point D on the hypotenuse. Well, that point is in a special place so that CD is perpendicular to AB. Anyone know what it's called when you make a line segment going from a vertex towards another side in such a way that it's perpendicular to the other side? It's actually not an angle bisector. It is an altitude. It could be an angle bisector if, like, if it was an isosceles triangle, it would be an angle bisector of the angle C. But in this case, see how angle C is kind of split into, it doesn't seem like it's split into 45, 45. So it's called an altitude. Now, if I tell you in this picture, there is a way to find the length of the altitude, if I know, let's say the whole thing is 13, I'm told that. Well, that's not enough information. But if I also tell you the pieces, or if I don't tell you the 13, if you have these three pieces of information, there is a way to calculate out the length of the altitude. And it's a little tricky to see, so I'm just going to pretend for a second that this is like a 40-degree angle, just to help you see this. If this was 40 degrees, this here would be 50 degrees, because we have a right angle here. But since this is also a right angle, this would have to be 40 degrees. And since this is a right angle, this is also, so that would make this 50 degrees. And that would always happen, that this number would equal this number, and this number would equal that number. Now, there are three triangles in this picture. There is the large, there is, sorry, what's that? Highlighted. There is the large ABC triangle. There is the medium-sized ACD triangle. And there is the small CBD triangle. And what do you notice about the medium and the small and the large triangle? What do you observe about those three triangles? Well, the altitude, yeah, they're all right triangles, and the altitude is the side of both the small and the medium side. But yes, that comment that just came up, they're all similar triangles. All three triangles, the big yellow one is 40, 90, 50. The green, oh, I see, that became green because of the mixing of the colors. That's, oh wow, that's a cool looking pen. I'm gonna make this one, they're all similar triangles. And that's really important because since we have similar triangles, if you don't mind, I'm gonna draw them side by side now. So this is the big one that has the 40 up here and the 50 there, and the X is like its base. I'm sort of rotating that triangle, and the 9 is here. And then I'll take this small one and orient it the same way, but now the 50 is here. This one doesn't change, and I'm just translating it down. It's this one, this green one that I rotated. And I have a 4 here, but you see the X here? That's this side, but that's also this one here. So it ends up, now if I do proportions, I get 9 over x equals x over 4, or x squared equals 36, or x equals 6. in general, let me take a new page to draw this nice and neat. In general, if you have this situation, has to be a right triangle. If you have this situation, no, don't use, we wouldn't know the, we may not know the angle. So in that other case, we knew the angle, but even if it's not a 50-degree angle, oops, let me call this A. That's the length from here to here, and B. So if you have these three pieces of information, A, here, B is just this piece there, and A is this piece here. It will always be true that A over X equals X over B. In other words, AB is equal to X squared. Or X is equal to the square root of AB. And that will only work if this angle is a right angle. Why is that? What if it's not a right angle? Why doesn't it work anymore? What's wrong with this if it's not a right angle? Why can't we just do the same reasoning if the angle's not a right angle? That's right. They won't be similar triangles anymore. I could even specifically say, like, if this was 50 and this was 40, I wouldn't be able to say that that was 50 and go through that process. So the configuration, we must have a right angle here. But if you have this configuration and you see this, you can say, you could jump straight to this proportion if you want, or you could even jump straight to that if you want. So that's one of our theorems. That's a pretty famous theorem. They say the altitude drawn to the hypotenuse is what's called the mean proportional between the pieces of the hypotenuse. Anyway, there was a while they would teach this to kids in like 8th grade, like pretty recently, and it would always be a question on the 8th grade state test, which I didn't think was necessary to have this. It's not that important of a theorem to come up in real life. Here's the last slide. What this last slide shows is that it kind of lets us see those two triangles. When they're all together, it's very hard to see which sides are corresponding sides. But when you separate the triangles out, this X down here, that's X and that's X, because both of them are that side. So that's the shared side, is the unknown. Okay, you good on slide 8? Can I go to the next one? So this is yet another like fact, and on like a test, if I make like a final exam or some sort of delta math activity, this would be a perfectly reasonable question, 5, 20, X, like that. This is not drawn to scale. What would the answer be then? And yes, it would be 10. X is the square root of 5 times 20 is the square root of 100. When you have an expression like A over X equals X over B, just to give you a definition, they say that X is what's called the mean proportional. You don't really have to know that, except that sometimes when they describe this theorem, they say X is the mean proportional. So mean proportional means you could set up this proportion where there'd be an X here and here. Yes, there could be non-perfect squares, but sometimes when it's not a perfect square, I might ask, what's the value? Like, let's say I say like 3 and 8 and x. I might just ask, what's x squared? In that case, it's just 3 times 8. Oops, I really better put those there. Often, when it's not a perfect square, I'm asking about x squared. We'll see. The reason I'm showing you this theorem today is because it's something you need for one of the historical things I'm going to show you in a few minutes. Okay. Now, Euclid's Elements, I mentioned, came out in 300 BC. And the structure of Euclid's Elements is there are 13 books, and the books are divided into propositions. And each proposition is a construction. Well, not each. Many of the propositions are teaching you how to use a compass and a straight edge to produce geometric shapes. And the things that aren't constructions are like theorems that they use to prove that the construction actually achieved what it said it was going to. And just for historical reasons, I'm going to bring back my web browser. And I think it's important to know that the Euclid's Postulates. So Euclid's Elements, you can't start proving things about geometry until you set down some like rules. Well, and then you use the rules to prove stuff. And Euclid starts the Elements with 5 postulates. These are like the ground rules of all the proofs that are going to happen. And it's real famous. So like from a historical point of view, the idea of Euclid's 5 postulates, it's like, I say Euclid's like this great writer, and he could have had more postulates, but he wanted to have the smallest possible list of postulates, because if you could prove something, then you don't need to make it a postulate. A postulate is something you don't prove. It's something that we just say, okay, here, we're just going to say these things are true, because you can't prove these things. So here they are. Number 1 says a straight line segment can be drawn joining any 2 points. That's what lets you take a straight edge, which is like a ruler, but it doesn't have any markings on it, and lets you draw line segments. Any straight line can be extended indefinitely in a straight line. Given any straight line segment, a circle can be drawn having the segment as radius and one endpoint as the center. So if you have a compass, you're allowed to use it to make circles. And then number 4, all right angles are congruent. So they seem like pretty basic. But then you have postulate 5. And this is a complete mouthful. If 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect each other on that side if extended far enough. It's like, which one of these doesn't belong? Well, I just wanted to let you know that without postulate 5, they're not able to prove like certain things like the Pythagorean theorem. So they reluctantly make it a postulate. Later on, thousands of years later, people trying to show that you could prove postulate 5 from the other 4, it wasn't possible. So then in the 1800s, they said, what if we reject postulate 5 and only prove things where it don't depend on it? Or what if it's not true And they invented things called non-Euclidean geometry, where triangles have more than 180 degrees or less than 180 degrees, depending on how you're changing Postulate 5. So from historical purposes, you should know there's a thing called Postulate 5. It's extremely controversial. Postulates 1 through 4 aren't controversial at all. There's also Euclid's common notions. Those are things that are those aren't controversial at all. Things which equal the same thing equal one another. That's like transitive property. If equals are added to equals, then wholes are equal. You certainly use that in algebra a lot. If equals are subtracted from equals, the remainders are equal. Things which coincide with one another equal one another. Those are just common notions. So Euclid's Elements has 13 books, and maybe it has about 800 propositions. I don't know how many. How many in Euclid's Elements? 800? Let's see. In Euclid's just curious. Well, they're only saying about book 1. Book 1 has 48 propositions. I know that. But how many altogether? No. Not sure how many propositions there are. Here we go. 465 propositions in Euclid's Elements. Book 1, proposition 1 is a construction. So let me go back to the iPad for a second. Okay. So you know it's important if Euclid teaches it, uses it as book 1, proposition 1. And it is, how can you use a compass and a straight edge to produce an equilateral triangle if you're given a line segment that's going to be one of the sides of the triangle? And this is important, and I'm going to show you how to do it. If you have a compass with you, you can do it. I think for homework I have you try to do that. And if you don't have a compass, you can survive without it. Here we go. Let's here. I'm going to call this thing Thales. I'll give you access to all these. Thales Theorem. And now I'll make a new construction. So here's my line segment. And here's how we do it. Step 1. One of the postulates says that you can make a circle with any point you want as the center and any line segment you want as the radius. So if I come here and I click on endpoint and I make a circle, and then I come here and make a second circle. And as you can see, these two circles intersect actually at 2 places, but let's just concentrate on this one. If I move the point near the intersection, it will snap onto the intersection. And then when I connect points, I get this thing. And if you don't believe that it's equilateral triangle, measure the 3 angles. I can change the size. And you can see no matter what I do, it continues to be an equilateral triangle. I'll say Euclid 1.1. back in the day, people memorized almost like the Bible, chapters and verses. And you would say, you know, what gives you, you know, by what reason is this? Or what did you do? And they would know Euclid 1, book 1, proposition 1, 1.1 is the construction of the equilateral triangle. Every theorem had a book and a proposition number, and you would use those as your reasons in geometric proofs. You wouldn't have to write things like vertical angles are equal. You would just say 1.7, and everyone just knew, they memorized. So it was a lot easier to do geometry proofs because you didn't have to write things like all vertical angles are equal. You could just have the book and proposition memorized and refer to it that way. Thousands of years they did that. Okay, let's go back to the iPad for a second. Here's a good thought-provoking question for you. How do you know that it works? It's not just because I measured the angles and it became 60-degree angles. Why must this construction produce equilateral triangle? You could type in, why don't I put some letters here? If I'll call this A, B, and C. So why must triangle ABC be equilateral? Well, C is not on line segment AB. You are right that C is like above the midpoints of A and B, but how do we prove it? Yes, and I see there, it's because, not because of the angles, but it's because line segment AB must be the same length as line segment AC, because those are both radii of the circle with A in the center. But CB is a radius of the circle with B in the center, so it has to equal AB also. It's equilateral. Equilateral means sides are equal. It's also true that the angles are equal, but the official equilateral, lateral stands for sides. So all three sides must be equal. And notice how, this is book 1, proposition 1. It was dependent on one of the common notions that all radii of a circle are congruent. And that's how Euclid starts the elements, with a very nice construction. It actually gets really hard in book 1, proposition 2, which we're going to skip that one because there are other propositions, but it is kind of, if you get excited to read Euclid's elements, and book 1, proposition 1 is kind of easy and you're feeling good, you'll want to skip book 1, proposition 2, because it's not a very important one. It's really hard. Okay, let's go to some more constructions. I'm going to jump now to Euclid book 1, proposition 10, which is how to use a compass and a straight edge to find the midpoint of a line segment. Now, we don't just get the midpoint, but we get the so-called perpendicular bisector. But since the perpendicular bisector goes through the midpoint, we'll have, so we won't just have a point, we'll have an entire line. And I'm going to teach you how to do that. I'm going to go back to Desmos. This Desmos thing is great. New construction. This one is going to be, I'll just call it midpoint. Well, I could get fancy. Euclid 1.10. You do not have to memorize book and proposition of Euclid unless you want to. So here I have a line segment. And here are the steps. We make a circle like this. We basically do the same construction as the equilateral triangle. Okay, what do you think the final step is of this construction? Where? That's right. I'm gonna make a segment that connects this top point, which would be like make the equilateral, and connect that point. That line segment will be the perpendicular bisector. We haven't proved it yet. I'm telling you that it is. And that makes this point here the midpoint. Oh, do they not? This does not have a measurement tool? I can't believe it. I'm shocked. Let me see. Ah, there it is. So to measure it, I'm going to have to make a segment from here to here and a segment from here to here. And now I can double click on this and I can say add label. So that's 2.53. And here I do the same thing. And as you can see, it is the midpoint. And if you're wondering, well, how do we know it's the perpendicular bisector? Well, this doesn't prove it, but at least for this example. So it does seem to be a perpendicular bisector. Let's see if we can prove that. Because basically what Euclid's Elements does is they present a construction, and they prove that it actually accomplished what they were trying to prove. A little bigger. Forget about this 0.8. I don't know why I have that there. Okay, let me just examine this for a second. If I draw in these line segments, hold on a second. I create these two triangles. Oh, that's not the picture. No wonder why something was wrong. Sorry about that. That was one. Sorry for this. Now I'm going to draw in a bunch of these things, and I'm going to draw this. Let me just examine this a little bit more, just to make sure I have this right. Now, this triangle on the left, this isosceles triangle, is going to be so-called congruent to this triangle on the right-hand side. And by congruent, I mean that the three sides are equal. That's what, remember before I mentioned side, side, side? SSS is a shorthand that says that if you have two triangles and all you know about them for sure is that all three sides are equal to each other, you don't need to measure the angles also. They're the same triangle. SSS is a fancy way of saying you don't need to know all 6 things about it, because there are also these 3 angles, right? 1, 2, 3. You don't need to know that the angles are equal. Side, side, side tells you that if the 3 sides are equal, then the 3 angles are also going to be equal. So these 2 like obtuse triangles are equal to each other. What that means, once you know that these 2 obtuse triangles are equal, then you're allowed to say that all the other 3 pieces, the angles and all, are equal. So then you're allowed to say that this angle and this angle are also equal. Because of side, 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 we can now say the angles are definitely equal also. Now I'm going to focus my attention on these 2 triangles. That one and that one. Now those triangles are congruent because of another reason, which is called SAS. SAS means that this side equals this side is part of both, and the angle between them are also equal. SAS means that if you have 2 sides equal and the angle between them, then the other 3 pieces of the triangle are also equal, the other side of the other 2 angles. So that would mean, because this triangle on the left, the little one, is equal to this triangle on the right, that would mean that also these 2 pieces would have to be equal, the sort of third side. And if the third side's equal, then that point must be the midpoint. It's okay if you don't remember your side, 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 your SAS. I'm more interested that you know how to do the construction, but I do want to like show you that that the construction does work and there's a reason why it works. But for our purposes, I'm just more interested that you know how to do the construction. So we can bisect an angle. I'm sorry, a side to get the midpoint. The next construction I want to show you is how to construct an angle bisector. I'm going to go back to Desmos geometry. Save this. I'll call the next one Euclid. It's like showing off to do this. Euclid 1-9. I really should just call it Angle Bisector Construction. Okay, so I'm going to create an angle, just a random angle. And so we need to find an angle bisector. Step 1 is to make a circle with the center at the vertex of the angle. And don't make the circle too big. We want it to intersect both of the sides, so it doesn't matter how big you make it, as long as it's small enough that it hits both sides of the angle. And I purposely made the other side on this length. I mean, I guess if this side was shorter, that would be too long. I'd want to make it short enough, but I can extend these. Okay, that's step 1. Step 2 is to get this point here. And then step 3 is to make a little, see these 2 points here? Make a little equilateral triangle on that by going like this and like that. And this is the 3rd point. So this, I'm not going to make this 3rd side because we don't need it, but I could if I wanted to. So that would be equilateral triangle. And then I would connect as a ray, I guess. I'll make it a line segment. This to this. And if I go ahead and measure this angle, it's 18 degrees. If I measure this angle, it's also 18 degrees. And if I change the side of the original angle, whoops, you can see that this angle bisector construction works. On the homework, I actually have you, if you have a compass, if you don't have a compass, you can do it on Desmos, I guess. You can do it by hand, even without a compass. Okay, back to the iPad to see why this works. Here's the picture. And what if I clean it up a little bit? Now, these two sides have to be equal because those sides came from here. See the circle here? So those two lines were both radii of the original circle. That's why those are equal. And why are these two things equal? You can type it in. I'm sure those are equal also. Why is that? That's right. Remember, and it's also because I have equilateral triangle, but it's an equilateral triangle because of the congruent, these two circles here, this one and this one, those are congruent circles. They both have as their radius this line. I didn't draw in that line, but that's the radius of both circles. This equilateral triangle has to have these two sides equal. And this side in the middle, you should put an X there, that's shared by both. So SSS tells me that this triangle here, obtuse triangle, is congruent to this triangle here. And that means that not only are the three sides equal, but the three angles are also equal, namely this one and that one. You might remember from geometry, Cpctc, corresponding parts of congruent triangles are congruent. That's basically saying that once you've verified that the two triangles are equal because of SSS or SAS, you can then say what you want about the other pieces that weren't mentioned already. And that is the angle bisector construction. Okay, there's two more constructions for today. The next construction is split a segment into n equal pieces. So like we know how to do a midpoint. Well, if I want to cut it into 4 pieces, I could just take a midpoint and then, you know, more midpoints. But what if I want to cut it into 3 equal pieces? Well, you can't do that with midpoints. You'll never get thirds. So I'm going to show you what the process is for splitting a line segment into n equal parts. This is actually, believe it or not, this is actually book 6, proposition 9. because it involves similar triangles, and he doesn't get to similar triangles until book 6, so he holds off on this one. They usually says the book in Roman numerals. Okay, so here I have a line segment. And I want to cut it into 3 pieces or 4 or 5 pieces or something like that. Step 1 is to make a ray starting from one of the points and going off in any direction that you want. Doesn't matter. Step 2 is to pick a point on that ray anywhere you want. I usually make it kind of close to this point. You'll see why in a second. Step 3 is to make a circle from that point to the first one. And step 4 is to make a circle from the intersection and finally I stop here. Well, what I've done so far is notice how this here, these are this piece, and this piece are all equal. I can even, I think I would have to, I'm going to hide this segment now and replace it with 3 separate segments. And I can measure these. This is my first time using Desmos. I usually use something called GeoGebra. This one's really simple to use compared to GeoGebra. Anyway, well, this line segment here is divided into 3 equal pieces, but the original one is not. So what you do is you make a line segment from here to here, forming a triangle. And then, more tools. In Euclid's Elements, one of the constructions in book 1 is how to make parallel lines. So let's just assume that we know how to do that already, or you could just do it by like eyeballing it. I make a line that's parallel to this third side, but goes through this point. And then another one that's also parallel to this and goes through that point. And then I find the intersections here and here. And if this was done right, I'm going to hide this. When you hide as opposed to delete, it just turns invisible. But if you delete it, it messes up the construction. I'm going to replace it with 3 line segments. And then those line segments, I go back to select here, and I'll go add label, add label, add label. And what you see is that if I take the original line segment and change it, it is trisected, split into 3 pieces. If I chose a different, if I chose a different angle, see, it wouldn't matter. If I took this point and put it low or way up high, it wouldn't matter. Does anyone want to say in the comments, is a 2-word reason for why this construction works? I'll put the iPad back. what two-word construction would explain why that works? I mean, 2 words probably wouldn't be enough, but like if someone didn't understand it, those 2 words wouldn't be convincing to them. But why does this construction work, do you think? That's right. Similar triangles formed by the parallel lines. You see this little tiny triangle? This little tiny triangle is similar to this medium-sized triangle, is similar to this large triangle. Because you only need 2 angles for triangles to be similar, and they all have this angle in the corner. But because of these parallel lines, these angles are all congruent. Now, remember this, I'm going to go like this. This is, I'm going to call this, let's just pretend that this is 1, and this would be 2. That would be 3. So basically, the little triangle is half as big as the medium triangle and 1/3 as big of the large triangle. So if this is 1 and that's 2 and that's 3, these are all equal, but that would make this 1, 2, 3. In other words, those sides would have to be equal also. So I can cut a line segment into as many parts as I want with this trick. Now, if I ask you to do it for homework, you can make the parallel lines just by like approximating them with a ruler. Okay, now we are at the last thing for today, which is from Book 2, Proposition 14. And it's a construction where you're given a rectangle, and the goal is to use your compass and straight edge, to produce a square whose area is exactly the same as the rectangle. And I'm going to take you through the steps for that one. Back to this. I'm going to post all these. This is going to be okay. We're going to need a rectangle first. So I'm going to make a line segment. Now, to make it a rectangle, I am going to need a right angle. So perpendicular line, go like that. And I'll put a point on that perpendicular line. And then I'll do, I'll make another perpendicular line to make the top side of the rectangle. And then I'll make another perpendicular line here. And that will be the 4th point. I am going to hide, not delete, but hide all these lines except for the one on the bottom. And I'm going to replace them with line segments. So there's a rectangle. If I go to the polygon tool, I can shade it in. And if I shade it in, I'll bet if I click on it, I'll have the option of the area. So the area of this rectangle is 16.98. Now I want to make a square whose area is 16.98. So here come the steps. It's about 7 steps. Step 1, extend the bottom side by making a ray here. Step 2, I want to, step 2 is to make a circle from this corner up to the top. And step 3 is to make this point here. Now, the thing I want you to notice is that, and I wonder, can I label these points? Label? There we go. If we have our points labeled, we'll have to talk about this stuff more easily. Okay, in the comments, what can you say about AB and AC at this point? Yes, they're equal because they're both radii. Now, I'm going to hide this big line segment and replace it. I'm actually going to hide this line segment also. And I'm instead going to draw a line segment all the way from E to B. And now I'm going to make the midpoint of EB. Remember, book 1, proposition 10, we learned how to make a midpoint. So if you were given the rectangle, so far, all you had to do is extend EA, make a circle, and then you'd have to do the whole construction to get the midpoint, but here we just have the midpoint. The next step is to go from this new midpoint you just got and make a big circle here. I am, if you don't mind, I'm going to hide this circle because it's kind of like in the way. So far, all I've done is made circles and I found a midpoint. The next step I'm going to make is I'm going to go from A to C, make a ray. The construction is not hard to do. What's hard is to understand why it works. This point here, where AC extended hits the circle, is a very important point. So important that I'm going to label it. AG, I'm now going to make a square that has AG as one of its sides. To do that, easiest thing to do is to extend AB and make a circle with A as the center and G. See how AG is the radius? So that means if I make a point right here, that will be another point on the circle. That circle I just made, I'm going to hide it because it's just in the way. I'm going to leave this other circle there. This point will be the corner of the square. And finally, I need that last corner. Well, this has tools for perpendicular lines. So if I go perpendicular to that bottom line and perpendicular to this line through here, I get that point. I'll label that point also. Just to clean up my diagram a bit, I'm going to hide these long lines. And I'm going to replace them with line segments. And check this out. I'm going to shade in the square, click on all 4 points in order, and go back to the original one. And as the grand finale, the area. It's the same. Check this out.
Oh my goodness.
That's pretty neat. Make a square. See how that square on the right? Can I make a different color? I think I can. That's right. You were one step ahead of me there. Grand finale. How awesome is that? Now you might think, oh wow, how did that work? It's like magic, it's like wizardry. Well, good news for you. It's not hard to prove this one. It's actually easier than the other ones. Here comes the iPad back, then we'll be done for today. Okay, here's the picture. Imagine that the dimensions of the rectangle were 9 by 4. How big is this side that I'm pointing to? I didn't name that point on this picture. How big is this side that I'm shading in like that? You remember how that point came about? The endpoint of the diameter? How big is that in this picture? Yes, it's 4 because it's the same as this. It was created to be that way. Now, I'm going to draw in 2 lines. What can you say about angle AF? Just, can I call this point N so we can say it? Angle AFN? What was the first geometric theorem we did this class? Yes, it's 90 degrees. Failies Theorem says that. So we're getting to use Thales Theorem now. And then, if I draw, these are right angles, I draw this, I put an X here. What do you notice there? What can you do to figure out what X is? Yes, it's that similar triangle thing. You remember? Yes. So X squared is equal to 9 times 4. Remember this picture? Right angle, AB, X, X squared equals AB. Well, this square has X as all of its sides. So its area is 9 times 4, which is the same as the area as the rectangle. And that's why this square, if you do this construction, will always have the same area because of this property. But this property only works because of Thales Theorem. That had to be a right angle. And the similar triangles. And the sneaky thing was bringing the 4 from over here to over here before I made the circle. Anyway, that's one of my favorite theorems in, that's one of my favorite theorems in geometry. Before I let you go, I'm going to do a quick epilogue. If it's not a square, a rectangle, but it's a triangle, the trick is to find the midpoints of the base of the triangle, and then this rectangle will have the same area. That looks like a square. Let me make a rectangle that's a little more rectangular looking. So you go to the midpoint of the side, and you go to the same height there. So this rectangle will have the same area as the triangle, because the triangle is 1/2 base times height. So if you make a rectangle with half the base, it's going to have the same area. And then you go through the construction to square the rectangle. And then the square, the rectangle, and the triangle will all have the same area. And as the final thing, if you have some kind of weird quadrilateral, you could split it into 2 triangles. And then you square each of the triangles by first making them rectangles and then making them into squares. And then you can take those 2 squares and you can put them together with the Pythagorean theorem and get the area, a square that's equal to the area of the whole thing. And you can actually keep doing that even if you had any polygon that can be split up into triangles. The triangles become squares, and the 2 squares at a time can get added together. Anyway, that's a little epilogue. If you understood this, I'm happy. The things that I wanted you to learn today, it was a big day. Well, we did a lot of stuff. But this last thing was just an epilogue. This is not really important for us. I just wanted to mention it. We learned a lot of constructions today. We did 5 constructions. Constructing equilateral triangle, midpoint, angle bisector, splitting a line segment into n equal pieces, and so-called squaring the rectangle. In order to understand these proofs, we had to know about isosceles triangle, we had to know about Thales theorem, we had to know about similar triangles, we had to know about SSS and SAS got used in the proofs. So big day, that's why it took a long time. I will post this all, I would say the video will be up within about 2 hours, hour maybe. Okay, so that's good for today. If you haven't done geometry in a while, your head's gonna be spinning, but I hope that I did a good job.